Okay, in this episode we're going to be looking at guide sheet number 5, and we're going to be trying to visualize the electric fields that are created by various charges. A few conventions that go along with that, things we always do the same. We always assume electric field lines begin on positive charges and terminate on negative charges. It's going to be the direction that a positive test charge will be moved if it's allowed to move within the field. The number of lines that emanate from a charge or approach a charge depends on the magnitude of the charge, so it depends on Q. The bigger the Q, the bigger the charge, the more lines will be drawn from it. The smaller the charge, the less lines will be drawn from it. At locations where a line meets the surface of a charge, the lines are drawn perpendicular, which would be radial, to the charge. And the strength of the electric field is greatest wherever the lines are closest together. So the lines will be closest together near the surface of the charge, and just like with gravity, where the local gravitational field strength is largest closest to the planet, same thing with electric fields. Okay, so we can start figuring out which one of these are. Now an A is emanating outward away from charge A, so it must be positive. It's terminating on charge B, so it must be negative. Charge C, it emanates outward, so it must be positive. Charge D, it's going in, so it must be negative. This is an electric dipole kind of situation. E, they're going into E, it's terminating on E, so that makes that negative. They're coming out of F, so that makes that positive. G, they're emanating out of G, so they're positive. H, it's also emanating out. And I, it's also emanating out. So those are all positive. Notice that creates two dead spots here and here. And notice that the charges are not equal in the amount. H would have the largest, G would be the next, and then I would be last. So we're going to use that idea of the number of lines indicating the charge strength to rank these charges. So in A, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 lines emanating from A. And with B, it's 1, 2, 3, 4, 5, 6, 7, 8. So A is more than twice as strong as B. In terms of type of charge, A would be positive, B would be negative. This one again, I'm not going to try to count all of those, but there are certainly many more in the D charge than there are in the C charge, and they're coming out from the D, so D is positive and C is negative. In this one, E, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. G, 1, 2, 3, 4, 5, 6. So G is the weakest. E, it would be next. And then F, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, has 12 on the lower half, so another 12 would make it the strongest. Now, these are really jam-packed in here, but it looks like J has the fewest. H would be next, and then I, they're really jammed together in there. I would think that would be the most. So it looks like I, H, J in terms of strength. Okay, if we're going to draw the configuration, again, it would go out from the positive. Now, it would try to go out here into a straight line, but the other charge is going to pull it across. So I would get something like that. On the right-hand side, I would get something like that. They're out of the positive into the negative. Oops, sorry, that's left. Ones that are like this area might come around here and sweep along. This one a little bit on the right-hand side, sweep around. Again, plus. This one here. This one here. This one way out here might just go away from the negative charge. One here would be headed out, would start to curve. If you draw these further out, one thing, they do not cross each other. Okay, now these two are negative. This is going to look very similar, but it's going to be directionally the opposite, because it's going to go out of the positive and into the negative. So the directions of the field are exactly the reverse of what they were before. Now these three are all positive. Now the field should stretch out directly this way, but as it interacts with the other field, it's going to end up with, that shouldn't hit the other one. It's positive, they're all out. Same kind of thing on this side. As this one heads out, it's going to get repelled away. This one heads out, it's going to get repelled away. They should be symmetrical. My drawing is not the best. This one heads out, gets repelled away. This one heads out, gets repelled away. That leaves a big dead spot here in the middle of those particular charges. Now, if we line a whole bunch of charge up, what we end up with is simply a line of a group of equally spaced lines, which tells us that the electric field here in the center is constant, uniform throughout. This would be what we would have if we had two parallel plates of conductors, like two metals, as in a battery or a capacitor. If we have four positive charges, we're going to end up with the same kind of thing we did with the three. It's going to go out, 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 out, and out. And they are out away from the positive, so the fields are all outward. Again, that still leaves a big dead spot in the middle. The difference here is we have these four sections where it's pushed away as opposed to the three sections we had before. Now, if we try to put a lot of positive charge on the outside, like a sphere, this one is going to repel this one. These two electric fields are going to essentially wipe each other out. So what we're going to have is something that's going to take us back to where we were very early on. Essentially, this is going to act exactly the same as if it was a point charge. Okay, our very first look was a positive point charge. Now, notice that makes a big zero field in here. This is why you're safe in a car in a lightning storm. If the car is made of metal, any charge can't get inside that shape. And no electric field can be created inside this metal conductor. It's just electrically, it's a big dead spot. So, electric field lines, which are an idea from Michael Faraday back at the turn of the 18th and 19th century, early 19th century. Ways to think about which way the charges would be moved, so they're called lines of force. Gives you some idea of getting a sense of the interaction between the different fields. If you draw the equipotentials, the places of equal potential, they're going to be perpendicular to those lines, the electric field lines. Okay, that's it for electric field.